Hello everyone, welcome back. I'm your friend in Saxo. Today we're going to know this section.
Trigonometry.
Trigonometry. You know what? We heard this a lot when we are in the high school. We often hear them say such as sine, cosine, and tangent. For me, it's just a nightmare to hear all those words because I don't know anything about them, especially when I am in an examination. But for now, since our difference, since I start to become a master of knowledge learning, so whatever, let's get into it.
What I have attempted to draw here is a unit circle. And the fact that I'm calling it a unit circle means it has a radius of 1. So this length from the center, and I centered it at the origin, this length from the center to any point on the circle is of length 1. So what would this coordinate be right over there, right where it intersects along the x-axis? Well, it would be x would be 1, y would be 0. What would this coordinate be up here? Well, we've gone 1 above the origin, but we haven't moved to the left or the right. So our x value is 0, our y value is 1. What about back here? Well, here our x value is -1. We've moved 1 to the left, and we haven't moved up or down. So our y value is 0. And what about down here? Well, we've gone a unit down, or 1 below the origin, but we haven't moved in the xy direction. So our x is 0 and our y is -1. Now with that out of the way, I'm going to draw an angle. And then the way I'm going to draw this angle, I'm going to define a convention for positive angles. I'm going to say a positive angle, well, the initial side of an angle, we're always going to do along the positive x-axis. So this is you can kind of view it as the starting side of the angle, the initial side of an angle. And then to draw an angle, a positive angle, the terminal side, we're going to move in a counterclockwise direction. So positive angle means we're going counterclockwise. And this is just the convention I'm going to use, and it's also the convention that is typically used. And so you can imagine a negative angle would move in a clockwise direction. So let me draw a positive angle. So a positive angle might look something like this. This is the initial side, and then from that I go in a counterclockwise direction until I measure out the angle, and then this is the terminal side. This is a positive angle theta. And what I want to do is think about this point of intersection between the terminal side of this angle and my unit circle. And let's just say it has the coordinates a, comma, b. The x value where it intersects is a, the y value where it intersects is b. And the whole point of what I'm doing here is I'm going to see how this unit circle might be able to help us extend our traditional definitions of trig functions. And so what I want to do is I want to make this theta part of a right triangle. So to make it part of a right triangle, let me drop an altitude right over here, and let me make it clear that this is a 90-degree angle. So this theta is part of this right triangle. So let's see what we can figure out about the sides of this right triangle. So the first question I have to ask you is, what is the length of the hypotenuse? What is the length of the hypotenuse of this right triangle that I have just constructed? Well, this hypotenuse is just a radius of a unit circle. The unit circle has a radius of 1, so the hypotenuse has length 1. Now, what is the length of this blue side right over here? This blue side, you could view this as the opposite side to the angle. Well, this height is the exact same thing, as the y coordinate of this point of intersection. So it's this height right over here is going to be equal to b. The y coordinate right over here is b. This height is equal to b. Now, exact same logic. What is the length of this base going to be? The base just of the right triangle. Well, this is going to be the x-coordinate of this point of intersection. If you were to drop this down, this is the point x is equal to a, or this whole length between the origin and that is of length a. Now that we have set that up, what is the cosine? And what is the cosine? Let me use the same green. What is the cosine of my angle going to be in terms of a's and b's and any other numbers that might show up? Well, to think about that, that, we just need our SOHCAHTOA definition. That's the only one we have now. We are actually in the process of extending it. SOHCAHTOA definition of trig functions. And the ka part is what helps us with cosine. It tells us that the cosine of an angle is equal to the length of the adjacent side over the hypotenuse. So what's this going to be? The length of the adjacent side for this angle, the adjacent side has length a, so it's going to be equal to a over what's the length of the hypotenuse? Well, that's just 1. So the cosine of theta is just equal to a. Let me write this down again. So the cosine of theta is just equal to a. It's equal to the x-coordinate of where this terminal side of the angle intersected the unit circle. Now let's think about the sine of theta. Sine of theta. And I'm going to do it in, well, let me see. I'll do it in orange. So what's the sine of theta going to be? Well, we just have to look at the SO part of our SOHCAHTOA definition. It tells us that sine is opposite over hypotenuse. Well, the opposite side here has length b, and what the hypotenuse has length 1. So our sine of theta is equal to b. So an interesting thing, this coordinate, this point where our terminal side of our angle intersected the unit circle, that point AB, we could also view this as a is the same thing as cosine of theta, a is the same thing as cosine of theta, and b is the same thing, as sine of theta. Well, that's interesting. That was just, we just used our SOHCAHTOA definition. Now, can we in some way use this to extend SOHCAHTOA? Because SOHCAHTOA has a problem. It works out fine if our angle is greater than 0 degrees, if we're dealing with degrees, and if it's less than 90 degrees. We can always make it part of a right triangle. But SOHCAHTOA starts to break down as our angle is either 0 or maybe even becomes negative, or as our angle is 90 degrees or more. You can't have a right triangle with two 90-degree angles in it. It starts to break down. Let me make this clear. So sure, so this is a right triangle, so the angle is pretty large. I can make the angle even larger and still have a right triangle even larger, but I can never get quite to 90 degrees. At 90 degrees, it's not clear that I have a right triangle anymore. It all seems to break down. And especially the case what happens when I go beyond 90 degrees. So let's see if we can use what we set up here. Let's set up a new definition of our trig functions, which is really an extension of SOHCAHTOA, and is consistent with SOHCAHTOA. Instead of defining cosine as, if I have a right triangle and saying, okay, it's the adjacent over the hypotenuse, sine is the opposite over the hypotenuse, tangent is opposite over adjacent, why don't I just say, for any angle, I can draw it in the unit circle using this convention that I just set up. And let's just say that the cosine of our angle is equal to the x-coordinate where we intersect, is equal to the x-coordinate where the terminal side of our angle intersects the unit circle, where angle, I'll write the terminal side of angle intersects the unit circle. And why don't we define sine of theta to be equal to the y-coordinate where the terminal side of the angle intersects the unit circle. So essentially, for any angle, this point is going to define cosine of theta and sine of theta. And so what would be a reasonable definition for tangent of theta? Well, tangent of theta, even with SOHCAHTOA, could be defined as sine of theta over cosine of theta, which in this case is just going to be the y-coordinate where we intersect the unit circle over the x-coordinate. In the next few videos, I'll show some examples where we use a unit circle definition to start evaluating some trig ratios. SOHCAHTOA could be defined.
Okay, there has nothing new about it. If the hypotenuse, this side equal to 1, then for the sine zeta, property is equal to zeta, it's equal to the b. And for the cosine, it's equal to the x, cosine zeta. And for the tangent, it's just equal to the y over x, which means sine over cosine. Yeah, that's something that we know.
On the right-hand side, we have a bunch of expressions that are just ratios of different information given in these two diagrams. And then over here on the left, we have the sine taken of angle MKJ, cosine of angle MKJ, and tangent of angle MKJ. And angle MKJ is this angle right over here, same thing as theta. So these two angles have the same measure. We see that right over there. And what we want to do is figure out which of these expressions are equivalent to which of these expressions right over here. And so I encourage you to pause the video and try to work this through on your own. So assuming you've had a go at it, So let's try to work this out. And when you look at this diagram, it looks like the intention here on the left is this evokes the unit circle definition of trig functions, because this is really this is a unit circle right over here. And this evokes kind of the SOHCAHTOA definition, because we're just kind of in a plain vanilla right triangle. And so just to remind ourselves, let's just remind ourselves of SOHCAHTOA, because I have a feeling it might be useful. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we can refer to this, and we can also remind ourselves of the unit circle definition of trig functions, that the cosine of an angle is the x-coordinate, and that the sine of where this ray intersects the unit circle, and the sine of this angle is going to be the y-coordinate. And what we'll see through this video is that they're actually, the unit circle definition is just an extension of SOHCAHTOA. So let's look first at x over 1. So we have x is the x-coordinate. That's also the length of this side right over here. Relative to this angle, theta, that is the adjacent side. So x is equal to the adjacent side. What is 1? Well, this is a unit circle. 1 is the length of the radius, which for this right triangle is also the hypotenuse. So if we apply the SOHCAHTOA definition, x over 1 is adjacent over hypotenuse. Adjacent over hypotenuse. Adjacent over hypotenuse, that's cosine. So that's going to be, this is equal to cosine of theta. But theta is the same thing as angle MKJ. They have the same measure. So cosine of angle MKJ is equal to cosine of theta, which is equal to x over 1. Now let's move over to y over 1. Well, y is going to be the length of this side right over here. Y is going to be, let me do this in the blue. Y is going to be this length relative to angle theta. That is the opposite side. That is the opposite side. Now, which trig function is opposite over hypotenuse? Opposite over hypotenuse, that's sine of theta. Sine of theta. So sine of angle MKJ is the same thing as sine of theta. We see that they have the same measure. And now we see that's the same thing as y over 1. Now for both of these, I use the SOHCAHTOA definition, but we could have also used the unit circle definition. X over 1, that's the same thing. That's the same thing as x. And the unit circle definition says, well, this point, the x-coordinate of where this, I guess you could say the terminal side of this angle, this ray right over here, intersects the unit circle, that by definition, by the unit circle definition, is the cosine of this angle. X is equal to the cosine of this angle, and the unit circle definition, the y-coordinate is equal to the sine of this angle. We could have written this as, instead of x comma y, we could have written this as cosine of theta, sine theta, just like that. But let's keep going. Now we have x over y. We have adjacent over opposite. So this is equal to adjacent over opposite. Tangent is opposite over adjacent, not adjacent over opposite. So this is the reciprocal of tangent. So this right over here, if we had to, this is equal to 1 over tangent of theta. And we later learn about cotangent and all of that, which is essentially this. But it's not one of our choices. So we can rule this one out. But then we have y over x. Well, this is looking good. This is y is opposite, x is adjacent relative to angle theta, adjacent. So this is the tangent of theta. This is equal to tangent of theta. So tangent of angle MKJ is the same thing as tangent of theta, which is equal to y over x. Now let's look at j over k. So j over k. Now we're moving over to this triangle, j over k. So relative to this angle, because this is the angle that we care about, j is the length of the adjacent side, and k is the length of the opposite side, So this is adjacent over opposite. So this is equal to adjacent over opposite. Tangent is opposite over adjacent, not adjacent over opposite. So once again, this is a reciprocal of the tangent function, not one of the choices right over here. So we can rule that one out. Now k over j. Well, now this is opposite over adjacent. Opposite over adjacent. That is equal to tangent of theta. This is equal to tangent of theta, or tangent of angle MKJ. So this is equal to k over j. Now we have m over j. M over j. Hypotenuse over adjacent side. This, of course, is equal to the hypotenuse. Hypotenuse over adjacent. Well, if it was adjacent over hypotenuse, we'd be dealing with cosine, but this is the reciprocal of that. So this is actually 1 over the cosine of theta, not one of our choices here, so I'll just rule that one out right over there. Then we have its reciprocal, j over m. That's adjacent over hypotenuse. Adjacent over hypotenuse is cosine. So this is equal to cosine of theta, or cosine of angle mkj. So we could write it down. So this is equivalent to j over m. And then one last one, k over m. Well, that's opposite over hypotenuse. Opposite over hypotenuse. That's going to be sine of theta. So this right over here is equal to sine of theta, which is the same thing as sine of angle mkj, which is the same thing as all of these expressions. So this is equal to k over m. And we are done.
Right, that I guess the two videos that we just watched are just trying to tell us how to define the sine and cosine based on the ratio of two side lengths, I guess, both instead of a triangle. Right, let me get into the next one, radians.
You are by now probably used to the idea of measuring angles in degrees. We use it in everyday language. We've done some examples on this playlist where if you had an angle like that, you might call that a 30 degree angle. If you have an angle like this, you could call that a 90 degree angle, and we'd often use this symbol just like that. If you were to go 180 degrees, you'd essentially form a straight line. Let me make these proper angles. If you go 360 degrees, you have essentially done one full rotation. And if you watch figure skating on the Olympics and someone does a rotation, they'll say, oh, they did a 360, or especially in some skateboarding competitions and things like that. But the one thing to realize, and it might not be obvious right from the get-go, but this whole notion of degrees, this is a human constructed system. This is not the only way that you can measure angles. And if you think about it, you say, well, why do we call a full rotation 360 degrees? And there are some possible theories, and I encourage you to think about them. Why does 360 degrees show up in our culture as a full rotation? Well, there's a couple of theories there. One is ancient calendars, and even our calendar is close to this, but ancient calendars were based on 360 days in a year. Some ancient astronomers observed that things seemed to move 1/360th of the sky or per day. Another theory is the ancient Babylonians liked equilateral triangles a lot, and they had a base 60 number system, so they had 60 symbols. We only have 10. We have a base 10. They had 60. So in our system, we like to divide things into 10. They probably like to divide things into 60. So if you had a circle and you divided it into about 6 equilateral triangles, and each of those equilateral triangles you divided into 60 sections because you have a base 60 number system, then you might end up with 360 degrees. What I want to think about in this video is an alternate way of measuring angles. And that alternate way, even though it might not seem as intuitive to you from the get-go, in some ways is much more mathematically pure than degrees. It's not based on these cultural artifacts of base 60 number systems or astronomical patterns. To some degree, an alien on another planet would not use degrees, especially if the degrees are motivated by these astronomical phenomena, but they might use what we're going to define as a radian. There's a certain degree of purity here. Radians. So let's just cut to the chase and define what a radian is. So let me draw a circle here. My best attempt at drawing a circle. Not bad. And let me draw the center of the circle. And now let me draw this radius. And let's say that this radius, and you might already notice the word radius is very close to the word radians, and that's not a coincidence. So let's say that this radius, the circle has a radius of length r. Now let's construct an angle. I'll call that angle theta. So let's construct an angle theta. So let's call this angle right over here theta. And let's just say, for the sake of argument, that this angle is just the exact right measure, so that if you look at the arc that subtends this angle, and that seems like a very fancy word, but let me draw the angle. So if you were to draw the angle, so if you look at the arc that subtends the angle, that's a fancy word, but that's really just talking about the arc along the circle that intersects the two sides of the angles. So this arc right over here subtends angle, the angle theta. So let me write that down. Subtends subtends angle theta. Let's say theta is the exact right size, so that this arc is also the same length as the radius of the circle. So this arc is also of length r. So given that, if you were defining a new type of angle measurement and you wanted to call it a radian, which is very close to a radius, how many radians would you define this angle to be? Well, the most obvious one, if you kind of view a radian as another way of saying radiuses, or I guess radii, well, you say, look, this is subtended by an arc of 1 radius, so why don't we call this right over here 1 radian? Why don't we call this 1 radian? Which is exactly how a radian is defined. When you have a circle and you have an angle of 1 radian, the arc that subtends it is exactly 1 radius long, which you can imagine might be a little bit useful as we start to interpret more and more types of circles. With when you give it degrees, you have to do a little bit of math and think about the circumference and all of that to think about how many radiuses are subtending that angle. Here, the angle in radians tells you exactly the arc length that is subtending the angle. So let's do a couple of thought experiments here. So given that, what would be the angle in radians if we were to go, so let me draw another circle here. That's the center. We'll start right over there. So what would happen if I had an angle? What angle, if I wanted to measure in radians, what angle would this be in radians? And you can almost think of it as radiuses. So what would that angle be? Going 1 full revolution in degrees, that would be 360 degrees. Based on this definition, what would this be in radians? Well, let's think about the arc that subtends this angle. The arc that subtends this angle is the entire circumference of this circle. It's the entire circumference. Of this circle. Well, what's the circumference of a circle in terms of radiuses? So if this has length r, if the radius is length r, what's the circumference of the circle in terms of r? Well, we know that. That's going to be 2 pi r. 2 pi r. So going back to this angle, what's the length of the arc that subtends this angle is how many radiuses? Well, it's 2 pi radiuses. It's 2 pi times r. So this angle right over here, I'll call this let's call this angle x. X in this case is going to be 2 pi radians. And it is subtended by an arc length of 2 pi radiuses. If the radius was 1 unit, then this would be 2 pi times 1, 2 pi radiuses. So given that, let's start to think about how we can convert between radians and degrees and vice versa. If I were to have, and we can just follow up over here, if we do 1 full revolution, that is 2 pi radians. How many degrees is this going to be equal to? Well, we already know this. A full revolution in degrees is 360 degrees. Well, I could either write out the word degrees or I can use this little degree notation there. Actually, let me write out the word degrees. It might make things a little bit clearer that we're kind of using units in both cases. Now, if we wanted to simplify this a little bit, we could divide both sides by 2, in which case we would get on the left-hand side, we would get pi radians would be equal to how many degrees? Well, it would be equal to 180 degrees. 180 degrees. And I could write it that way, or I could write it that way. And you see over here, this is 180 degrees. And you also see, if you were to draw a circle around here, we've gone halfway around the circle. So the arc length, or the arc that subtends the angle, is half the circumference. Half the circumference are pi radiuses. So we call this pi radians. Pi radians is 180 degrees. And from this, we can come up with conversions. So 1 radian would be how many degrees? Well, to do that, we would just have to divide both sides by pi. And on the left-hand side, you'd be left with 1. I'll just write it singular now. 1 radian is equal to, I'm just dividing both sides. Let me make it clear what I'm doing here, just to show you this isn't some voodoo. So I'm just dividing both sides by pi here. On the left-hand side, you're left with 1. And on the right-hand side, you're left with 180 over pi degrees. So 1 radian is equal to 180 over pi degrees, which is starting to make it an interesting way to convert them. Let's think about it the other way. If I were to have 1 degree, how many radians is that? Well, let's start off with, let me rewrite this thing over here. We said pi radians is equal to 180 180 degrees. 180 degrees. So now we want to think about 1 degree. So let's solve for 1 degree. 1 degree, we can divide both sides by 180. We are left with pi over 180 radians is equal to 1 degree. So pi over 180 radians is equal to 1 degree. This might seem confusing and daunting, and it was for me the first time I was exposed to it, especially because we're not exposed to this in our everyday life. But what we're going to see over the next few examples is that as long as we keep in mind this whole idea that 2 pi radians is equal to 360 degrees, or that pi radians is equal to 180 degrees, which is the two things that I do keep in my mind, we can always rederive these two things. You might say, hey, how do I remember if it's pi over 180 or 180 over pi to convert the two things? Well, just remember, which is hopefully intuitive, that 2 pi radians is equal to 300.
All right. So what he did inside of this video is to introduce you a new unit to define an angle, I guess.
Radius, circumference.
Okay, here's a word called circumference. And how can we get the circumference for a circle? Well, here an expression or formula for that. They call it 2 pi times r. The r here is a radius. What is a radius? It's a right line right in here inside of a circle. And what's interested? What's the right expression to say that? But the interesting part for that is what's the 360 degrees or radians right in here? The unit would be, it's also equal to 2 pi times the radians. And I guess there must have some relationships between the radians and the
360 degrees. And we'll work through a bunch of examples in the next video to just make sure that we're used to converting.
There must have some relationships between the radius, this word, and the radian. There must have some relationships between the two. Okay, here what it said. More generally, the magnitude in radians of a subtended angle is equal to the ratio of the arc length to the radius of the circle. That is zeta equal to S over R, where zeta is a subtended angle in radians, S is the arc length, R is the radius. What's that mean? Here's another one. Radians, like degrees, are a way of measuring angles. 1 radian is equal to the angle formed when the arc opposite the angle is equal to the radius of the circle. Okay, so finally I got the idea. As you could say, right now we got a picture, right? And for this picture, for the radius we got
Radians and radius.
Okay, so for the radius we got for this side, we got the r as the length of that. And what's the radian for that? It's also equal to r. I mean, this side is also have the length of r, and this side is also have the length of r. They are equal. So that's why we call it right radian, because the radius and the radian arc have the same length. And clearly, if you look at this graph, you would know for the 180 degrees, we can somehow separate it to 3 radian, then left with 0.14. If we add them together, that will be just equal to pi. So that's why pi radians equal to 180 degrees. And that's also why for 4 circle, the 4 degree of circles, which is 360 degrees, it should be equal to 2 pi radians. And for this picture, it's even more obvious that it says that the anchor length just equal to the radius. For that's how we define the 1 radian that unites. And also here's another description. It also says 1 radian is a measure of the central angle whose arc length is the same as the radius of the circle. So if you look at this image, you could definitely have a clear idea what's the radian and how it related to the radius. Okay, that's it. Let's go back.
Let's see if we can give ourselves a little bit of practice converting between radians and degrees and radians. And just as a review, let's just remind ourselves of the relationship. And I always do this before I have to convert between the two. If I do one revolution of a circle, how many radians is that going to be? Well, we know one revolution of a circle is 2 pi radians. And how many degrees is that if I do one revolution around a circle? Well, we know that that's 360. I can either write it with a little degree symbol right like that, or I could write it just like that. And this is really enough information for us to think about how to convert between radians and degrees. If we want to simplify this a little bit, we can divide both sides by 2, and you could have pi radians are equal to 180 degrees. Or another way to think about it, going halfway around a circle in radians is pi radians. Or the arc that subtends that angle is pi radiuses. And that's also 180 degrees. And if you want to really think about, well, how many degrees are there per radian, you can divide both sides of this by pi. So if you divide both sides of this by pi, you get 1 radian. 1 radian, it would have to go from singular or from plural to singular. 1 radian is equal to 180 over pi degrees. So all I did is I divided both sides by pi. And if you wanted to figure out how many radians are there per degree, you could divide both sides by 180. So you'd get pi over 180 radians. Radians is equal to 1 degree. So this is, now I think we are ready to start converting. So let's convert 30 degrees. Let's convert 30 degrees to radians. So let's think about it. So I'm going to write it out. And actually, this might remind you of kind of unit analysis that you might do when you first did unit conversion, but it also works out here. So if I were to write 30 degrees, and this is how my brain likes to work with it, I like to write out the word degrees. And then I say, well, I want to convert to radians. So I really want to figure out how many radians are there per degree. So let me write this down. I want to figure out how many radians do we have per degree? How many radians do we have per degree? And I haven't filled out how many that is, but we see just the units will cancel out. If we have degrees times radians per degree, the degrees will cancel out and I'll be just left with radians. If I multiply the number of degrees I have times the number of radians per degree, we're going to get radians. And hopefully that makes intuitive sense as well. And here we just have to think about, well, if I have, think of it this way, if I have pi radians, how many degrees is that? Well, that's 180 degrees. Comes straight out of this right over here. Pi radians for every 180 degrees, or pi over 180 radians per degree. But then this is going to get us to, we're going to get 30 times pi over 180, 30 times pi over 180, which will simplify to 30 over 180 is 1 over 6. So this is equal to pi over 6. Actually, let me write the units out. This is 30 radians, which is equal to pi over 6 radians. Now let's go the other way. Let's think about if we have pi over 3 radians. Pi over 3 radians, and I want to convert that to degrees. So what am I going to get if I convert that to degrees? Well, here we're going to want to figure out how many degrees are there. How many degrees are there per radian? And one way to think about it is, well, think about the pi and the 180. For every 180 degrees, you have pi radians. 180 degrees over pi radians, these are essentially the equivalent thing. Essentially, you're just multiplying this quantity by 1, but you're changing the units. The radians cancel out, and then the pi's cancel out, and you're left with 180 over 3 degrees. 180 over 3 is 60, and we could either write out the word degrees, or you can write degrees just like that. Now let's think about 45 degrees. So what about 45 degrees? And I'll write it like that just so you can figure it out figure out with that notation as well. How many radians will this be equal to? Well, once again, we're going to want to think about how many radians do we have per degree. So we're going to multiply this times, well, we know we have pi radians. We know we have pi radians for every 180 degrees. For every 180 degrees, or we could even write it this way: pi radians for every 180 degrees. And here, this might be a little less intuitive, the degrees cancel out, and that's why I'd like to usually write out the word, and you're left with 45 pi over 180 radians. Actually, let me write this with
all right. All right. So, this video is kind of boring. You know, what I did is totally based on the equation that we have, and I guess this kind of calculation is quite basic. So I just leave it there. Then what is this?
The Pythagorean identity.
The Pythagorean identity. I don't know shit about it. So let's get it started with it.
So let's review the unit circle definition of trig functions a little bit. Right over here, I've drawn a unit circle. And when we say unit circle, we're talking about a circle with radius 1. So for example, this point right over here is the point 1, 0, x is equal to 1, y is 0. This point is the point 0, 1. This is the point negative 1, 0, and this is the point 0, negative 1. That the radius over here, the distance from the center of the circle, which is at the origin, to any point in the circle, or any point on the circle, I should say, this radius is equal to 1. So the unit circle definition of trig functions leverages this unit circle. That's why it's called the unit circle definition. And we saw that if we define an angle as the kind of bottom side of the angle being along the positive x-axis, and then the other side of that angle, thinking about where it intersects the unit circle, so let's say that this is the angle theta, we define sine of theta and cosine of theta, or cosine theta and sine of theta, as the x and y coordinates of this point at which this side of the angle, the side that is not the positive x-axis, where that intersects the unit circle. So for example, this point right over here, if we would call this the x-coordinate of this point, so this value right over here, we would call that cosine of theta. We would call that cosine of theta. And the y-coordinate of that point, which is this point right over here, we would call that sine of theta. And in previous videos on the unit circle, we talked about why this is really just a natural extension of the SOHCAHTOA definition. What's useful is it starts to work for negative angles, it works for angles, it even works for 90-degree angles, it works for angles more than 90 degrees, it works for angles less than 90 degrees. So it's really, really, really useful. But what I want to do is leverage what we already know about the unit circle definition of trig functions to help prove the Pythagorean identity. It almost falls out of the fact that this point right over here is on a circle of radius 1. So what is the equation of a circle with radius 1 centered at the origin? Well, the equation of that is x squared. We have other videos where we really prove this using the distance formula, which is really just an application of the Pythagorean theorem. The equation of a circle, of a unit circle centered at the origin, is x squared plus y squared is equal to 1, is equal to the radius squared. This distance right over here is equal to 1. Well, we've already said that we're defining cosine of theta as the x-coordinate of this point, and we're defining sine of theta as the y-coordinate of this point, and this point is sitting on the circle. It has to satisfy this relationship right over here. So that means, well, if we're defining cosine of theta to be the x, to be this x value, sine of theta to be the y value, and it has to satisfy this relationship, that means that cosine of theta squared plus sine squared of theta plus sine squared of theta needs to be equal to 1, or sine squared theta plus cosine squared of theta needs to be equal to 1. And that's just from the point. This is the x, cosine theta is the x coordinate, sine theta is the y coordinate. They have to satisfy this relationship which defines a circle. So cosine squared theta plus sine squared theta is 1. Now, this is called, as we've seen in other videos, this is called the Pythagorean identity. And you say, why is that useful? Well, using this, if you know sine of theta, you can figure out what cosine of theta is going to be, or vice versa. And if you know one of cosine of theta, and then you could, or say you know cosine theta, then you use this to figure out sine of theta, then you could figure out tangent of theta, because tangent of theta is just sine over cosine. But if you're a little bit confused as to why this is called the Pythagorean identity, well, it really just falls out of where even the equation of a circle even came from. If we look at this point right over here, which we're saying is the x-coordinate is cosine theta and the y-coordinate is sine of theta, what is the distance between that point and the origin? Well, to think about that, we can construct a right triangle. So this distance right over here, and so that we can deal with any quadrant, I'll make it the absolute value of the cosine theta is this distance right over here. And this distance right over here is the absolute value of the sine of theta. The absolute value of the sine of theta. And I obviously don't have to take the absolute value for this first quadrant here, but if I went into the other quadrants and I were to set up a similar right triangle, then the absolute value is at play. And so what do we know from the Pythagorean theorem? This is a right triangle here. The hypotenuse has length 1. So we know that this expression squared, the absolute value of cosine of theta squared, plus this expression squared, which is this length, plus the absolute value of the sine of theta squared, needs to be equal to the length of the hypotenuse squared, which is the same thing, which is going to be equal to 1 squared. Or we could say, this is the same thing. If you're going to square something, the sine, if it's negative, it's going to be negative times a negative, so it's just going to be positive. So this is going to be the same thing as saying that the cosine squared theta plus sine squared theta is equal to 1. So once again, or I guess this is why it's called a Pythagorean identity. And actually, that's even where the equation of a circle comes from. It comes straight out of the Pythagorean theorem, where your hypotenuse it has length 1. So
Okay, now I have no doubts or confusing with the plan of Pythagorean. Sorry, let me try to read it again. Pythagorean formula. Well, it's just a formula that we are quite familiar when back into the high school. You know, we use this formula or equation a lot, but we don't know shit about it. I mean, the meaning behind of that. But now, since you got all the graph, you would know it just means the distance. You know, between this point and the original point. But when I'm trying to know that in the high school, I don't know the hidden meaning of that. You know, I just remember this formula or this equation, which is definitely not a good thing. So why you learn the math by only remembering those stuff? That makes sense. The mathematics is all about analyzing and logical rule or something like that. So it doesn't actually it doesn't only require you to memorize something. If you only do it by memory something, that's too bad. You have to know how to use it. I mean, how to use it to do some analyzation or calculation.
Let's say that we're told that some angle theta, which is going to be expressed in radians, is between negative 3 pi over 2 and negative pi. It's greater than negative 3 pi over 2, and it's less than negative pi. And we're also told that sine of theta is equal to 1/2. From this information, can we figure out what the tangent of theta is going to be equal to? And I encourage you to pause the video and try this on your own. In case you are stumped, I will give you a hint. You should use the Pythagorean identity, the fact that sine squared theta plus cosine squared theta is equal to 1. So let's do it. So we know the Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. We know what sine squared theta is. Sine theta is 1/2, so this could be rewritten as 1/2 squared plus cosine squared theta is equal to 1. Or we could write this as 1/4 plus cosine squared theta is equal to 1. Or we could subtract 1/4 from both sides and we get cosine squared theta is equal to, see, you subtract 1/4 from the left-hand side, then this 1/4 goes away. That was the whole point. 1 minus 1/4 is 3/4. So what could cosine of theta be? Well, when I square it, I get positive 3/4. So it could be the positive or negative square root of 3/4. So cosine of theta could be equal to the positive or negative square root of 3/4, which is the same thing as the positive or negative square root of 3 over the square root of 4, which is 2. So it's the positive or negative square root of 3 over 2. But how do we know which one of these it actually is? Well, that's where this information becomes useful. That's where this information actually becomes useful. Let's draw our unit circle. If you're saying, well, why am I even worried about cosine of theta? Well, if you know sine of theta, you know cosine of theta. Tangent of theta is just sine of theta over cosine theta. So then you will know the tangent of theta. But let's look at the unit circle to figure out which value of cosine we should use. So let me draw it. So unit circle, that's my y-axis. That is my x-axis. And I will draw the unit circle in pink. So that's my best attempt at drawing a circle. Please forgive me for its lack of perfect roundness. And it says theta is it's greater than negative 3 pi over 2. So where's negative 3 pi over 2? So let's see, this is negative pi over 2. So if this is one side of the angle, let me do this in a color. So let's see, this one side of the angle is going to be along the positive x-axis, and we want to figure out where the other side is. So it's going to, this right over here, that's negative pi over 2. This is negative pi. So it's between negative pi, which is right over here. So let me make that clear. Negative pi is right over here. It's between negative pi and negative 3 pi over 2. Negative 3 pi over 2 is right, negative 3 pi over 2 is right over here. So the angle, our angle theta is going to put us someplace over here. Someplace over here. And the whole reason I did this, so this whole arc right here, you could think of this as the measure of angle theta right over there. And the whole reason I did that is to think about whether the cosine of theta is going to be positive or negative. We clearly see it's in the second quadrant. The cosine of theta is the x-coordinate of this point where our angle intersects the unit circle. So this point right over here, this right over here, actually let me do it in that orange color again. This right over here, that is the cosine of theta. Now, is that a positive or negative value? Well, it's clearly a negative value. So for the sake of this example, our cosine theta is not the positive one, it is the negative one. So we can write that cosine theta is equal to the negative square root of 3 over 2. So we figured out cosine theta, but we still have to figure out tangent of theta. And we just have to remind ourselves that the tangent of theta is going to be equal to the sine of theta over the cosine of theta, Well, they told us the sine of theta is 1/2, so it's going to be 1/2 over cosine of theta, which is negative square root of 3 over 2. Negative square root of 3 over 2. And what does that equal? Well, that's the same thing as 1/2 times the reciprocal of this. So times negative 2 over the square root of 3. These 2's will cancel out, and we are left with negative 1 over the square root of 3. Now, some people don't like a radical in the denominator like this. They don't like an irrational denominator. So we could rationalize the denominator here by multiplying by square root of 3 over square root of 3. Square root of 3 over square root of 3. And so that gets us, this will be equal to negative square root of 3 over 3 is the tangent of this.
Okay, so what this video does is to teach you how can you use the Pythagorean this formula. He's trying to teach you how to use that formula, and also he teaches you how can you determine the sign of your sine zeta or cosine zeta by drawing a graph. And if inside of that angle range, your cosine zeta, if the x is let's say -1, then your cosine zeta should be a -1. If the x is a +1, then your cosine zeta should be a +1. And for the same thing for the y, if the y is positive, then your sine zeta should be positive, something like that.
So what we have depicted here is a unit circle centered at point A, and the point B lies on the circle, and then we dropped a perpendicular from point B to point D. Point D lies on the positive x-axis, and they form this triangle ABD. And they tell us that angle BAD, angle bad, it has a measure of pi over 4 radians. What I want to do in this video is use our knowledge of trigonometry and use our knowledge of triangles in order to figure out several things. So the first thing we want to figure out is what's the measure of angle, what's the radian measure of angle ABD, Actually, let's just do that first, and then I'll talk about the other things that we need to think about. So I assume you've paused the video and tried to do this on your own. So let's think about what ABD would be. We know two of the angles of this triangle, so if you know two of the angles of this triangle, you should be able to figure out the third. Now what might be a little bit unfamiliar, we're used to saying that the sum of the interior angles of a triangle add up to 180 degrees. But now we're thinking in terms of radians. So we could say that the sum of the angles of a triangle add up to, instead of saying 180 degrees is the same thing as pi radians. So this angle plus that angle are going to add up to pi. So let's just say that this right over here, let's just say measure of angle ABD in radians plus pi over 4 plus this is a right angle. What would that be in radians? Well, a right angle in radians, a 90-degree angle in radians, is pi over 2 radians. So plus pi over 2. When you take the sum of them, the interior angles of this triangle, they're going to add up to pi radians, which is, of course, the same thing as 180 degrees. And now we can solve for the measure of angle ABD. Measure of angle ABD is equal to pi minus pi over 2 minus pi over 4. I just subtracted these two from both sides. So this is going to be equal to, let's see, we could put a common denominator of 4. Then this is 4 pi over 4. This is minus 2 pi over 4. And this, of course, is minus pi over 4. So 4 minus 2 minus 1 is going to get us to 1. So this is going to give us 2 pi over 4. So the measure of angle ABD is actually the same as the measure of angle BAD. It is pi over 4. So that angle right over there is pi over 4. Now what does that help us with? So if we know that this is pi over 4, and that is pi over 4 radians, and once again, we know this is a unit circle. So we know that the length of segment AB, which is a radius of the circle, or is the radius of the circle, is length 1. What else do we know about this triangle? Can we figure out the lengths of segment AD and the length of segment DB? Well, sure. Because we have two base angles that have the same measure, that means that the corresponding sides are also going to have the same measure. That means that this side is going to be congruent to that side. I can reorient it in a way that it might make it a little easier to realize. If we were to flip it over, not completely flip it over, but if we were to make it look like this, so the triangle, we could make it look like, let me make it look a little bit more like this. Actually, I want to make it look like a right angle though. So my triangle, let me make it look like, there you go. So if this is D, this is B, this is A, this is our right angle. Now this is pi over 4 radians, and this is also pi over 4 radians. When your two base angles are the same, you know you're dealing with an isosceles triangle. An isosceles, but because they're not all the same, you know it's not equilateral. If all of the angles were the same, this would be equilateral. But this is an isosceles non-equilateral triangle. So if your base angles are the same, then you also know that the corresponding sides are going to be the same. These two sides are the same. This is an isosceles triangle. And so how does that help us figure out the lengths of the sides? Well, if you say that this side has length x, that means that this side has length x. If this side has length x, then this side has length x. And now we can use the Pythagorean theorem. We could say that x squared, this x squared plus this x squared is equal to the hypotenuse squared, is equal to 1 squared. Or we could write that 2x squared is equal to 1, or that x squared is equal to 1 over 2, or just taking the principal root of both sides, we get x is equal to 1 over the square root of 2. And a lot of folks don't like having a radical in the denominator. They don't like having a rational number in the denominator. So we could rationalize the denominator by multiplying by the square root of 2 over the square root of 2, which would be, let's see, the numerator will have the square root of 2, and in the denominator, we're just going to have square root of 2 times square root of 2 is just 2. So we've already been able to figure out several interesting things. We were able to figure out a measure of angle ABD in radians. We were able to figure out the lengths of segment AD and the length of segment BD. Now what I want to do is figure out what are the sine, cosine, and tangent of pi over 4 radians, given all of the work that we have done. So let's first think about what is the sine. Let me do this in a color, do it in orange. Given all the work we've done, what is the sine of pi over 4 radians? And I encourage you once again, pause the video, think about the unit circle definition of trig functions, and think about what this is. Well, the unit circle definition of trig functions, and this angle, this pi over 4 radians, is forming an angle with the positive x-axis, and where its terminal ray intersects the unit circle, the x and y coordinates of this point are what specify the cosine and sine. So the coordinates of this point are going to be the cosine of pi over 4 radians is the x coordinate, and the sine of pi over 4 radians is the y coordinate, sine of pi over 4. So what's the y coordinate going to be if we want the sine of pi over 4? Well, it's going to be this length right over here, which is the same thing as this length, which is the length of x, which is square root of 2 over 2. Now, what is the cosine of pi over 4? And once again, I encourage you to pause the video to think about it. Well, it's this x coordinate. What's the x coordinate? The x coordinate is this distance right over here, which is once again going to be x, which is square root of 2 over 2. Now, what is the tangent of pi over 4 going to be? Well, the tangent of pi over 4 is just sine of pi over 4 over cosine of pi over 4. Now, both of these are this exact same thing. They're both square root of 2 over 2. So you're going to have square root of 2 over 2 divided by square root of 2 over 2. Well, that's just going to give you 1. And that also makes sense because remember, the tangent of this angle is the slope of this line. And we see the slope. For every x we move in the horizontal direction, we move x up. So our change in y over change in x is essentially x over x, which is equal to 1.
Okay, while we nerd this video, it doesn't make sense for us to do that since it's just one part of the whole theorem that we nerded before. So what's the point of that? Alright, let's get into the next one. Graphs of sine, cosine, and tangent.
We're asked, what are the domain and range of the sine function? So to think about that, let's actually draw the sine function out. And what I have here, on the left-hand side right over here, I've got a unit circle. And let me truncate this a little bit. I don't need that space right there, so let me clear that out. So I have a unit circle on the left-hand side right over here, and I'm going to use that to figure out the values of sine of theta for a given theta. So in the unit circle, this is x, and this is y. Or you could even view this as we could just use it as x or y. And so for a given theta, we can see where that angle the terminal side of the angle intersects the unit circle, and then the y coordinate of that point is going to be sine of theta. And over here, I'm going to graph still y in the vertical axis, but I'm going to graph the graph of y is equal to sine of theta. Y is equal to sine of theta. And on the horizontal axis, I'm not going to graph x, but I'm going to graph theta. You can view theta as the independent variable here. And it's going to be theta is going to be in radians. So we're essentially going to pick a bunch of thetas and then come up with what sine of theta is and then graph it. So let's set up a little bit of a table here. And so over here I have theta. And over here, we're going to figure out what sine of theta is. And we could do a bunch of theta values. We could start, let's say we start at 0. Let's say we start at theta is equal to 0. What is sine of theta going to be? Well, when the angle is 0, we intersect the unit circle right over there. The y coordinate of this is still 0. This is the point 1, 0. The y coordinate is 0, so sine of theta is 0. Or we could say sine of 0 is equal to 0. Sine of 0 is equal to 0. Now let's try theta is equal to pi over 2. Theta is equal to pi over 2. I'm just doing the ones that are really easy to figure out. So if theta is equal to pi over 2, that's the same thing as a 90-degree angle. So the terminal side is going to be right along the y-axis, just like that. And where it intersects the unit circle is right over here. And what point is that? Well, that's the point 0, 1. So what is sine of pi over 2? Well, sine of pi over 2 is just the y coordinate right over here. It is 1. Sine of pi over 2 is 1. Let's keep going, and you might see a little pattern here. We're just going more and more around the circle. So let's think about what happens when theta is equal to pi. When theta is equal to pi, what is sine of pi? Well, we intersect the unit circle right over there. That coordinate is -1, 0. Sine is the y coordinate. So this right over here is sine of pi. Sine of pi is 0. Let's go to 3 pi over 2. 3 pi over 2. Well, now we've gone 3/4 of the way around the circle. We intersect the terminal side of the angle, intersects the unit circle right over here. And so based on that, what is sine of 3 pi over 2? Well, this point right over here is the point negative, let me be careful, is 0, -1. The sine of theta is the same thing as the y-coordinate, or the y-coordinate is sine of theta. So when theta is pi over 2, sine of theta, or when theta is 3 pi over 2, sine of theta is equal to -1. And let's come full circle. Let's come full circle here. So let's go all the way to theta equaling 2 pi. Let me do a color. Yeah, I'll just use the yellow here. What happens when theta is equal to 2 pi? Well, then we've gone all the way around the circle, and we are back to where we started. And the y-coordinate is 0, so sine of 2 pi is once again 0. And if we were to keep going around, we're going to start seeing, as we keep incrementing the angle, we're going to start seeing the same pattern emerge again. Well, let's try to graph this. So when theta is equal to 0, sine of theta is 0. When theta is equal to pi over 2, when theta is equal to pi over 2, sine of theta is 1. So we'll use the same scale. So sine of theta.
Alright, so I already figured out what this video will tell us. Well, basically, it will tell us the domain and the range of the sine function. Let's first talk about the range. So what's the y value would be for a sine function? Well, it would be the value that between 0 and, between the -1 and +1. That's the range of that function, of the sine function. And then what's the domain of it? Well, it can be anything from, to be honest, it can be anything. Here, as you could say, after he dropped that graph, he says that domain equal to the real numbers. Any real numbers would be fine.
We're asked, at how many points did the graph of y equals sine of theta and y equal cosine theta intersect for theta between 0 and 2 pi? And it's 0 is less than or equal to theta, which is less than or equal to 2 pi. So we're going to include 0 and 2 pi in the possible values for theta. So to do this, I've set up a little chart for theta, cosine theta, and sine theta, and we can use this to...
Alright, I have already guessed the result. It's probably only at the, let's say, pi over 4. At that time, we have the equal stuff. Oh, sorry, pi over 2. I made it wrong. Okay, so this is how it looks like. Oh, okay, pi over 4. I was right in here. As you can see, the cosine graph and the sine graph, they have an intersection point right on the x equal to pi over 4. And then if we add that by 1 pi, we got another intersection point. Amplitude, midline, and period.
Amplitude, midline, and period.
Okay, period. In the stock markets, we also have the amplitude.
We have a periodic function depicted here. What I want you to do is think about what the midline of this function is. The midline is a line, a horizontal line, where half of the function is above it and half of the function is below it. Then I want you to think about the amplitude. How far does this function vary from that midline? Either how far above does it go or how far does it go below? And it should be the same amount because the midline should be between the highest and the lowest points. And then finally, think about what the period of this function is. How much do you have to have a change in x to get to the same point in the cycle of this periodic function? So I encourage you to pause the video now and think about those questions. So let's tackle the midline first. So one way to think about it is, well, how high does this function go? Well, the highest y value for this function we see is 4. It keeps hitting 4 on a fairly regular basis, and we'll talk about how regular that is when we talk about the period. And what's the lowest value that this function gets to? Well, it gets to y equals -2. So what's halfway between 4 and -2? Well, you could eyeball it, or you could count, or you could literally just take the average between 4 and -2. So the midline is going to be the horizontal line. Y is equal to 4 plus -2 over 2. Just literally the mean, the arithmetic mean between 4 and -2, the average of 4 and -2, which is just going to be equal to 1. So the line y equals 1 is the midline. So that's the midline right over here. And you see that it's kind of cutting the function in. It's where you have half of the function is above it and half of the function is below it. So that's the midline. Now let's think about the amplitude. Well, the amplitude is how much this function varies from the midline, either above the midline or below the midline. And the midline's in the middle, so it's going to be the same amount whether you go above or below. So one way to say it is, well, at this maximum point right over here, how far above the midline is this? How far above the midline is this? Well, to get from 1 to 4, you have to go, you're 3 above the midline. Or another way of thinking about it, this maximum point is y equals 4 minus y equals 1. Well, your y can go as much as 3 above the midline. Or you could say your y value could be as much as 3 below the midline. That's this point right over here. 1 minus 3 is negative 1. So your amplitude right over here is equal to 3. You can vary as much as 3 either above the midline or below the midline. Finally, the period. And when I think about the period, I try to look for a relatively convenient spot on the curve. And I'm calling this a convenient spot because it's at a nice, when x is at negative 2, y is at 1, it's at a nice integer value. And so what I want to do is keep traveling along this curve until I get to the same y value, but not just the same y value, but the y value, I get to the same y value and I'm also traveling in the same direction. So for example, let's travel along this curve. So essentially, our x is increasing. Our x keeps increasing. Now you might say, hey, have I completed a cycle here? Because once again, y is equal to 1. You haven't completed a cycle here because notice over here, where our y is increasing as x increases, while here our y is decreasing as x increases. Our slope is positive here, our slope is negative here. So this isn't the same point on the cycle. We need to get to the point where y once again equals 1, or we could say, especially in this case, we're at the midline again, but our slope is increasing. So let's just keep going. Let's just keep going. So that gets us to right over there. So notice, now we have completed one cycle. So the change in x needed to complete one cycle, that is your period. So to go from negative 2.
So now we got the idea. First, the middle line, which is a horizontal line that will split all of your value into equally two parts. And for the amplitude, it's just the range your value would be in some extreme situation from the middle line. For example, here it is 3, which means no matter how big or how low your value is, it will always have a distance between the middle value, and that distance will not be beyond the number 3. And what is the word period? Well, it's just one cycle, or let's say a period of events, and that event, that graph will repeat itself over and over again as x increases. Transforming, say, what is that?
Transforming sinusoidal graphs.
Transforming sinusoidal graph.
Transforming sinusoidal graphs.
Transforming sinusoidal graphs. That's a difficult word. Sinusoidal.
Transforming sinusoidal graphs.
Transforming sinusoidal graphs. Yeah, I have no idea about that. Let's get into it.
We're asked to determine the amplitude and the period of y equals negative 1/2 cosine of 3x. So the first thing we have to ask ourselves is, what does amplitude even refer to? Well, the amplitude of a periodic function is just half the difference between the minimum and maximum values it takes on. So if I were to draw a periodic function like this, and it would just go back and forth between two, let me draw it a little bit neater. It goes back and forth between two values like that. So between that value and that value, you take the difference between the two, and half of that is the amplitude. Another way of thinking about the amplitude is how much does it sway? How much does it sway from its middle position? Right over here, we have y equals negative 1/2 cosine of 3x. So what is going to be the amplitude of this? Well, the easy way to think about it is just what is multiplying the cosine function, and you could do the same thing if it was a sine function. We have negative 1/2 multiplying it. So the amplitude in this situation is going to be the absolute value of negative 1/2, which is equal to 1/2. And you might say, well, why do I not care about the sign? Why do I take the absolute value of it? Well, the negative just flips the function around. It's not going to change how much it sways between its minimum and maximum position. The other thing is, well, how is it just simply the absolute value of this thing? And to realize the y, you just have to remember that a cosine function or a sine function varies between +1 and -1 if it's just a simple function. So this is just multiplying that +1 or -1. And so if normally the amplitude, if you didn't have any coefficient here, if the coefficient was positive or -1, the amplitude would just be 1. Now, you're changing it or you're multiplying it by this amount. So the amplitude is 1/2. Now let's think about the period. Let's think about the period. So the first thing I want to ask you is, what does the period of a cyclical function even, or a periodic function I should say, what does the period of a periodic function even refer to? Well, let me draw some axes on this function right over here. Let's say that this right over here is the y-axis. That's the y-axis, and let's just say, for the sake of argument, this is the x-axis right over here. So the period of a periodic function is the length of the smallest interval that contains exactly one copy of the repeating pattern of that periodic function. So what do they mean here? Well, what's repeating? So we go down and then up, just like that. Then we go down and then we go up. So in this case, the length of the smallest interval that contains exactly one copy of the repeating pattern. This could be one of the smallest repeating patterns. And so this length between here and here would be one period. Then we could go between here and here is another period. And there's multiple. This isn't the only pattern that you could pick. You could say, well, I'm going to define my pattern starting here, going up, and then going down like that. So you could say that's my smallest length. And then you would see that, okay, well, if you go in the negative direction, the next repeating version of that pattern is right over there. But either way, you're going to get the same length that it takes to repeat that pattern. So
you know what? It just reminded me the life of a human. So as a human, when we live, we will have the lowest point in our life, and we will also have the highest highlight moments at our life. But those just some experiments that we would have. So if you happen to be at the lowest point in your life, don't worry, you would go up. And if you are at the toppest part of that, you must feel it before, or you will feel in the future. And this is also applied for the stock market. Alright, here he even talked about the vertical strength and horizontal reflection.
We're asked to graph the function y is equal to 2 sine of negative x on the interval, the closed interval, so it includes the endpoints, negative 2 pi, a little bit obvious, it's just 2 pi, or you just see here that the period was 2 pi. It took 2 pi length. It looks something like that. And we could keep going in the negative direction. Negative side right over here between my little axes. Go from 2 sine of x.
Okay, what's the matter? What he was trying to do? Yeah, I don't see anything from it, so I just skip it. Graphing, say whatever function.
So we're asked to graph y is equal to 3 times sine of 1/2 x minus 2 in the interactive widget. And this is the interactive widget that you would find on Khan Academy. And it first bears mentioning how this widget works. So this point right over here, it helps you define the midline, the thing that you could imagine your sine or cosine function oscillates around. And then you also define a neighboring extreme point, either a maximum or a minimum point, to graph your function. So let's think about how we would do this. And like always, I encourage you to pause this video and think about how you would do it yourself. But the first way I like to think about it is, what would a regular if this just said y is equal to sine of x, how would I graph that? Well, sine of 0 is 0. Sine of pi over 2 is 1. And then sine of pi is 0 again. And so this is what just regular sine of x would look like. But let's think about how this is different. Well, first of all, it's not just sine of x, it's sine of 1/2 x. So what would be the graph of just sine of 1/2 x? Well, one way to think about it, there's actually two ways to think about it, is a coefficient right over here on your x term that tells you how fast the thing that's being inputted into sine is growing. And now it's going to grow half as fast. And so one way to think about it is, your period is now going to be twice as long. So one way to think about it is, instead of getting to this next maximum point at pi over 2, you're going to get there at pi. And you could test that. When x is equal to pi, this will be 1/2 pi. Sine of 1/2 pi is indeed equal to 1. Another way to think about it is, you might be familiar with the formula, although I always like you to think about where these formulas come from, that to figure out the period of a sine or cosine function, you take 2 pi and you divide it by whatever this coefficient is. So 2 pi divided by 1/2 is going to be 4 pi. And you can see the period here. We go up, down, and back to where we were over 4 pi. And that makes sense because if you just had a 1 coefficient here, your period would be 2 pi. 2 pi radians, you make one circle around the unit circle is one way to think about it. So right here we have the graph of sine of 1/2 x. Now what if we wanted to instead think about 3 times the graph of sine of 1/2 x, or 3 sine 1/2 x? Well, then our amplitude is just going to be 3 times as much. And so instead of our maximum point being at 1, it will now be at 3. Or another way to think about it is we're going 3 above the midline and 3 below the midline. So this right over here is the graph of 3 sine of 1/2 x. Now we have one thing left to do, and this is this minus 2. So this minus 2 is just going to shift everything down by 2. So we just have to shift everything down. So let me shift this one down by 2, and let me shift this one down by 2. And so there you have it. Notice our period is still 4 pi. Our amplitude, how much we oscillate above or below the midline, is still 3. And now we have this minus 2. Another way to think about it, when x is equal to 0, this whole first term is going to be 0, and y should be equal to -2. And we're done.
Okay, I guess by doing this kind of exercise, or let's say if we could answer those questions by using those little JavaScript widgets, I guess that would be fine for mathematics learning.
Sinusoidal models.
Sinusoidal models. This is the last part for today's video, but let's get into it.
We're told Alexa is riding on a Ferris wheel. Her height above the ground in meters is modeled by h of t, where t is the time in seconds. And we can see that right over here. Now what I want to focus on this video is some features of this graph. And the features we're going to focus on, actually the first of them, is going to be the midline. So pause this video and see if you can figure out the midline of this graph, or the midline of this function. And then we're going to think about what it actually represents. Well, Alexa starts off at 5 meters above the ground, and then she goes higher and higher and higher, gets as high as 25 meters, and then goes back as low as 5 meters above the ground, and as high as 25 meters. And what we can view the midline as is the midpoint between these extremes, or the average of these extremes. Well, the extremes are, she goes as low as 5 and as high as 25. So what's the average of 5 and 25? Well, that would be 15. So the midline would look something like this. And I'm actually going to keep going off the graph. And the reason is to help us think about what does that midline even represent. And one way to think about it is it represents the center of our rotation in this situation, or how high above the ground is the center of our Ferris wheel. And to help us visualize that, let me draw a Ferris wheel. So I'm going to draw a circle with this as the center. And so the Ferris wheel would look something like this. And it has some type of maybe support structure. So the Ferris wheel might look something like that. And this height above the ground, that is 15 meters. That is what the midline is representing. Now the next feature I want to explore is the amplitude. Pause this video and think about what is the amplitude of this oscillating function right over here, and then we'll think about what does that represent in the real world, or where does it come from in the real world. Well, the amplitude is the maximum difference, or the maximum magnitude away from that midline. And you can see it right over here at actually right when Alexa starts. We have starting 10 meters below the midline, 10 meters below the center. And this is when Alexa is right over here. She is 10 meters below the midline. And then after looks like 10 seconds, she is right at the midline. So that means that she's right over here. Maybe the Ferris wheel is going this way, at least in my imagination, it's going clockwise. And then after another 10 seconds, she is at 25 meters. So she is right over there. And you can see that she is right over there. I drew that circle intentionally of that size. And so we see the amplitude in full effect. 10 meters below to begin the midline, and 10 meters above. And so it's the maximum displacement or the maximum change from that midline. And so over here, it really represents the radius of our Ferris wheel, 10 meters. And then from this part, she starts going back down again. And then over here, she's back to where she started. Now, the last feature I want to explore is the notion of a period. What is the period of this periodic function? Pause this video and think about that. Well, the period is how much time does it take to complete one cycle. So here she's starting at the bottom. And let's see, after 10 seconds, not at the bottom yet. After 20 seconds, not at the bottom yet. After 30 seconds, not at the bottom yet. And then here she is. After 40 seconds, she's back at the bottom and about to head up again. And so this time right over here, that 40 seconds, that is the period. And if you think about what's going on over here, she starts over here 5 meters above the ground. After 10 seconds, she is right over here, and that corresponds to this point right over here. After 10 more seconds, she's right over there. That corresponds to that point. After 10 more seconds, she's over here. That corresponds to that. And after 10 more seconds, or a total of 40 seconds, she is back to where she started. So the period in this example shows how long does it take to complete one full rotation. Now, we have to be careful sometimes when we're trying to visually inspect the period, because sometimes it might be tempting to say, start right over here and say, okay, we're 15 meters above the ground. All right, let's see, we're going down. Now we're going up again. And look, we're 15 meters above the ground. Maybe this 20 seconds is a period. But when you look at it over here, it's clear that that is not the case. This point represents this point at being 15 meters above the ground, going down. That's getting us to this point, and then after another 10 seconds, we get back over here. Notice all this is measuring is half of a cycle, going halfway around. In order to go all the way around, not only do we have to get to the same exact height, but we have to be moving in the same direction. We're at 15 meters and going down. Here we're 15 meters and going up. So we have to keep going another 20 seconds in order to be 15 meters in the air and going down.
Then what's the matters? This is just the mental model in your brain. So this is how you understand this kind of, let's say, graph.
The longest day of the year in Juneau, Alaska is June 21st. It's 1,096.5 minutes long. Half a year later, when the days are at their shortest, the days are about 382.5 minutes long. If it's not a leap year, the year is 365 days long, and June 21st is the 172nd day of the year. Write a trigonometric function that models the length L of the tth day of the year. So it's going to be L as a function of t, assuming it's not a leap year. So I encourage you to pause this video and try to do this on your own before I try to work through it. So let me give a go at it. So instead of first starting at L of t, I'm going to actually start with L as a function of u, where u is another variable. I'll just use this kind of an intermediary variable that'll help set it up in a little bit of a simpler way, where u is days after June 21st. So let's just think about this a little bit. June 21st. If we're thinking about in terms of u is going to be equal to 0 because it's 0 days after June 21st. But if we're thinking about in terms of t, June 21st is the 172nd day of the year. It's 172. So what's the relationship between u and t? Well, it's shifted by 172 days. U is going to be equal to t minus 172. Notice when t is 172, u is equal to 0. So let's figure out L of u first, and then later we can just substitute u with t minus 172. So first of all, what's happening when u is equal to 0? Let me write all this down. So what is happening when u is equal to 0? Well, u equals 0 is June 21st, and that's the maximum point. So what trig function hits its maximum point when the input into the trig function is 0? Well, sine of 0 is 0, while cosine of 0 is 1. Cosine hits its maximum point. So it seems a little bit easier to model this with a cosine. So it's going to be some amplitude times cosine of, and let's say I'll write some coefficient c right over here. Actually, let me just use a b since I already used an a. Some coefficient over here times our u plus some constant that'll shift the entire function up or down. So this is the form that our function of u is going to take. And now we just have to figure out what each of these parts are. So first let's think about what the amplitude and what the midline is going to be. The midline is essentially how much we're shifting the function up. So let's get our calculator out. So the midline is going to be halfway between these two numbers. So we could say 1096.5 plus 382.5 divided by 2 gets us to 739.5. So that's what C is equal to. C is equal to 739.5. Now the amplitude is how much do we vary from that midline. So we could take 1096 minus this, or we could take this minus 382.5. So let's do that. So let's take 1096.5 minus what we just typed, what we just got, 739.5, and we get 357. So this is how much we vary from that midline. So A is equal to 357. So this right over here is equal to 357. So what's B going to be equal to? And for that, I always think about, well, what's the behavior of the function? What's the period of the function going to be? Let me make a little table here. So when u, let's put some different inputs from u. When u is 0, we're 0 days after June 21st. We're at our maximum point. And we already said that what we want the cosine function to evaluate to at that point is essentially we want it to evaluate as 357 times cosine of 0 plus 739.5. Now, what happens? What's a full period? Well, a full period is a year. At a year, we get to the same point in the year, which is, I guess, a little bit of common sense. So you go all the way to 365. You go all the way to, when u is 365, we should have completed a period. We should be back to that maximum point. So this should essentially be 357 times cosine of 2 pi. When do we, if we were just thinking in terms of a traditional trig function, if we just had just a theta in here, you complete a period every 2 pi. So this should be equivalent to what I'm writing out right over here, plus 739.5. So one way to think about it is b times 365 should be equal to 2 pi. Notice this is going to be b times 365. So let's write that down. B times 365 times 365, that's the input into the cosine function, needs to be equal to 2 pi. Or b is equal to 2 pi over 365. b is equal to 2 pi over 365. And we are almost done. We figured out what A, B, and C are. Now we just have to substitute u with t minus 172 to get our function of t. So let's just do that. So we deserve a little bit of a drum roll now. L of t is equal to.
Alright, so basically what this video does is tell us how can we model the real world problem into a math equation, into a math equation. So I guess this is, let's say, this is probably quite important because, by only know the sine, cosine, those concepts, it doesn't really help us that much if we cannot use it in real world. But I didn't see anyone use the sine cosine to solve the real world problems that much. But I guess I happen to know one. That is the cosine similarity. We use that formula, or we use this analogy to calculate the difference between two vectors or two matrices or two whatever. We use it in the natural language processing. If you don't know what I'm talking about, you can just leave it there. So basically, this is what we have learned today, and that's it. I will see you guys in the next video. Bye.